Hi, my name is Nicole Fern. I'm a senior hardware security engineer for Tortuga Logic, and I'm really excited to be here virtually with all of you to talk about how hardware can be a double-edged sword for security. One of the main messages of this talk is that hardware now more than ever is essential to consider in the context of security. If you plot the number of CVEs that have the word hardware in them over the years, you'll see a definite trend of increasing focus on hardware as a place where attackers are looking for vulnerabilities. And this is because hardware is truly a double-edged sword. It's relied upon as a trust anchor, but also can open systems up to attack. A key question in all of this is who wields the sword? Whose responsibility is it to secure hardware? Hardware is not designed in a vacuum. The hardware system is global, it's complex, it involves many different countries and organizations, and all of them have different motivations when it comes to hardware security. And this is what makes securing hardware incredibly challenging. So to start with, I want to talk a little bit more in detail about how hardware can be used to protect a system. And over the course of the next few slides, we'll see that while hardware security features are fantastic to include as protection for a larger system, to provide any security at all, these security features have to be implemented, configured, and used correctly, which is not always straightforward. Hardware is a natural choice to be used as a trust anchor because hardware can provide services such as cryptographic acceleration, secure storage in the form of one-time programmable memory, and a whole host of other things that are difficult, if not impossible, to provide using just software alone. We're seeing a definite trend towards using hardware subsystems that consolidate all of these security services and security functionality into one IP core that's can be sold to anyone developing a system on chip, commonly abbreviated as SoC. These roots of trust are subsystems focused exclusively on security, and what they provide to an SoC designer is the ability to kind of optimize the security subsystem for security and then leave the remaining portions of the system open to being optimized for things like performance. And so while this is great that we have dedicated IP being sold for security specifically, one thing to keep in mind is that it's not enough just to buy one of these hardware roots of trust from, for example, Rambus or Synopsys and just instantiate it in your design and assume you are secure. Purchasing and using security IP is kind of like buying a gate to secure your house. In this picture shown on the slide, the gate isn't providing any security because you can just walk through the lawn and circumvent it. But that's not to say that in a different system, in a different house, in a different context, that same gate might provide adequate security in a lawn with, for example, a fence or a wall surrounding it. And this is similar to what has to be true to secure an SoC. Of course, the security of an SoC depends on the security of the hardware logic itself, specifically the root of trust logic. But additionally, it's highly dependent on the hardware configuration and integration of that IP into the larger system. And also it's dependent on how software uses and configures security features. And this can be complex to analyze in the context of an entire system because vulnerabilities hide in design complexity and interaction between different system components. The Cisco Secure Boot hardware tampering vulnerability is a great example of a root of trust that was improperly integrated into a larger system. Cisco used an FPGA to provide the trust anchor for their entire device, the entire router. However, the FPGA bitstream, which completely controls the functionality of the FPGA, was stored unprotected in SPI flash and could be modified by an attacker. The flash region was not protected from privileged software rights from the application CPU, and it also wasn't encrypted. So it's fairly easy for an attacker to overwrite the bit stream to accomplish their own functionality, which had the consequence of completely bypassing secure boot or defeating secure boot, which is one of the main security services this root of trust was providing for the router. Earlier, I mentioned complexity, and one thing that makes hardware complex is that it's highly configurable. Hardware needs to be configurable for both flexibility reasons and also fixability reasons. If you can imagine, once a hardware design enters the physical world as silicon, it's really, really difficult, almost impossible to edit that functionality, right? Once the silicon is taped out, then that's it. If you find a problem or a security vulnerability with the hardware design itself, you have to work around it using things like microcode patches or firmware patches. Another option for providing configurability in hardware is registers. One common design practice is to use something called chicken bits. Chicken bits are kind of a special type of configuration register. They are undocumented bits on a device that can be used to disable certain functional security features, or more generally, any feature. So why would someone include chicken bits in their design? It provides the hardware designer the opportunity to chicken out of using a particular feature if a bug in the silicon in that feature is later discovered. But clearly this has security implications and ramifications. So the configuration space of hardware grows exponentially with design size, and this can make it really difficult to determine the impact of a specific configuration on security. Imagine you're trying to write the firmware for a hardware component that has 100 configuration bits. It's really difficult to determine, okay, which bits influence security, which bits influence functionality, and to get it right. And it's made even harder if the default values for those configuration bits in the registers lead to an insecure configuration. And that's exactly what happened in this BMC vulnerability, and that the default configuration resulted in the host CPU having arbitrary access to the BMC's entire memory space. So to mitigate this vulnerability, the firmware had to be updated to change the default configuration and secure the device. The debug infrastructure is another example of hardware that's typically configurable and also has an impact on the overall security posture of the device. Nailgun is a vulnerability that shows how certain insecure configurations of ARM's multi-core debug infrastructure can lead to privilege escalation that doesn't require physical access to the device. So in ARM's multi-core debug model, one core can be used as a debug host for another core. And so that's in contrast to the traditional debug model where the debug host is always an external debugger connected physically to the chip. This vulnerability can be prevented by setting these 4 configuration signals correctly. However, the authors of the Nailgun paper, they noted that a lot of devices that they looked at were set in the insecure configuration, and they guessed this is because it severely restricts the debug functionality if you put it in the secure configuration. So a lot of device vendors chose to just make it more flexible, more usable, more convenient, but ultimately insecure. Another important point that this paper brings up is that there are a lot of different parties involved that make decisions that influence security. So for this specific example, ARM provides the 4 signals in the architecture, the debug architecture. But then it's up to the SoC vendor, such as Qualcomm, who buys processors from ARM and incorporates them into their chip, they control how their customers set these for debug signals. Whether they're through fuses or through configuration registers or just hard-coded, that's up to the SoC manufacturer. And so their customers in the mobile device ecosystem, this would be the people making mobile phones such as Samsung or Google, they buy a chip from Qualcomm, and then it's up to them to set fuses at the factory to the correct values, or in their firmware stack, write secure values to the configuration registers. So it's pretty clear that security requires alignment across many stakeholders. Many companies and countries are involved in creating and using silicon chips, and it's not easy to point to any individual stakeholder and say, you are solely responsible for security. So we've talked about how hardware security features have to be configured and used correctly to provide security, but now I want to shift gears and talk about other hardware features that have nothing to do with security, but make systems vulnerable to attacks. I like to call this class of issue when functional features become security problems. There's a lot of complexity in modern hardware designs, which comes from, really demanding requirements for performance from consumers. We expect our devices to be extremely energy efficient, responsive, and always connected. And to do this, hardware designers have had to innovate a lot. And that's where you get things like direct memory access, speculation, et cetera, et cetera. And unfortunately, these functional performance features aren't always designed with security in mind. A great example of this is dynamic voltage and frequency scaling. DVFS is ubiquitous. It's critical for energy efficiency. What it is essentially is it's a mechanism that allows software to manage the power consumption of the device. So it can both modify and monitor power consumption. And it's good to do this because the operating system especially knows the workloads running on the device. They know what applications are running and how much power they need. So it's ideal for the operating system to control power consumption. But this has the consequence that the operating system can lower the voltage, increase the frequency, and inject faults during computation. This is extremely relevant if you are relying on a trusted execution environment, such as Intel SGX or ARM Trust Zone, to protect you against a potentially malicious operating system. Being able to monitor power consumption from software also has implications for security. The platypus attack showed that using the interfaces for monitoring power that are available to unprivileged software, you can perform a power side channel attack capable of recovering AES keys, kernel as their offsets, with no physical device access required. And that's pretty significant, because typically when you think of fault injection and power side channel attacks, you assume that the attacker has to have physical access to your device. Speculative and out of order execution is another great example of functionality added for performance reasons that is not transparent at all to the programmer's view of the processor, which that was okay until the discovery of Spectre and Meltdown, and then speculative execution, microarchitectural features were front and center with respect to security. And it's unfortunate that those features are so opaque, because not only addressing Spectre and Meltdown didn't involve only the processor vendors, it didn't involve only companies like Intel, AMD, and ARM. It required a lot of involvement and contribution from the software community as well, especially people developing compiler tool chains and operating systems. All of these groups had to work together to come up with mitigations in a timely manner for Spectre and Meltdown. So now that I've talked about all of the issues in hardware security, all of the challenges, in the final few moments of this talk, I want to present some solutions. The first of which is industry-wide hardware security initiatives. This category of solutions really is to address the challenge that security requires alignment between all the different stakeholders in the hardware ecosystem. And so to foster alignment and communication, you need these public initiatives that involve dozens and dozens of companies that are all contributing and working together. And I've listed a few of these on this slide if you're interested. Another solution that can be implemented by an individual company or organization is something called a hardware security development lifecycle. So this is for people who are designing hardware. And this addresses the challenge that security issues can arise at different design stages. So the idea is that you are going to, as an organization, dedicate resources to addressing security throughout the entire hardware development lifecycle. And by addressing it early on and consistently, you're going to reduce risk. And this is a good idea for organizations to implement, but it's easier said than done. There's a lot of technical challenges, and this is where I believe that technical solutions can really play a major role in making this feasible for companies to implement under really intense time to market pressure and resource constraints. So one technical solution to this problem I would like to bring up is hardware information flow analysis. This is the technology that I work with on a daily basis. So if you have any questions or this is something of interest to you, please come and speak with me after the session. A major problem that I see when people try to do security verification pre-silicon is that information flow is not a first-class concept in the existing tools, which makes it really, really awkward and really high effort to, first off, capture confidentiality and integrity requirements, which are so central to security. It's hard to capture those requirements in a way that you can actually verify in the context of your design implementation. So if you employ something like hardware information flow tracking, this streamlines the whole process and just makes it easier to specify and verify security requirements in hardware. And again, I'd be happy to talk with anyone after the session about this. So we've seen that there are a lot of requirements for securing hardware. First, because hardware is a double-edged sword, if you have security features implemented in hardware, that's great, but these features have to be implemented, configured, and used correctly. The other side of the coin is that features added in hardware to increase performance and usability really need to be considered from a security perspective. You can't just design functionality and assume that it's isolated from security, because it's hard to really argue that anything is really isolated from security. And lastly, security requires alignment across many different stakeholders, and there's just many different groups of people involved in securing hardware besides just the people designing the hardware. And so with that, I would like to leave all of these different groups and stakeholders with some questions to think about after the talk. If you're an IP provider or SOC vendor, what is your security strategy? Do you have a security strategy? Are you applying the same methodologies from functional verification to security? And are you struggling? If so, please come and talk with me after the session. Also, how are you communicating security with those using your hardware or IP? Is it easy for your customers to use your hardware in a secure way, or do they have to read through 500 pages of documentation to get it right? If you are an OEM or systems builder, do you understand how hardware can affect your threat model? And do you know how to configure and use the hardware in your device correctly? And lastly, if you're a software developer, you should be asking yourself, are you considering hardware in your threat model? Do you need to be considering hardware in your threat model? And this is because, in the past few years, we've seen attacks that were thought to require physical access to the device, for example, fault injection and side channel analysis. These attacks are being performed from software, which has implications if, for example, you are deploying something in the public cloud where there can be other tenants that share the hardware at the same time that your software is running. So with that, I'll leave you with the parting message that hardware is truly a double-edged sword, and we all wield it together. And I would be happy to take questions now.